And welcome everyone to this INNS webinar, the Helmholtz lecture by Sepp Hochreiter. I'm very much excited about that topic because maybe not everyone knows, but during my PhD, I was working on some very interesting models. When I started my PhD, actually, people told me hidden Markov models. That's what you need. All you need is hidden Markov models. And I luckily met some very bright guys who worked on some newer architecture called LSTM, long short-term memories. I think at the end of my PhD, I really much understood now LSTM, that's the way to go. Later on, like most of my PhD students realized, no, LSTM is not all you need. And then there is these hypes of, yeah, attention is all you need. But even that, maybe you have seen the news a few years back, has been also deprecated. Large language models, that's all you need. And there are discussions about that as well. Maybe not. There is more required. We need foundation models as well. And there's always these ups and downs in the history. But I was very much excited because this year, during summer, we had the IJCNN conference in Rome. And Sepp already gave a live keynote there, and he called it LSTM is so back. That was, of course, very exciting news for me. And we spoke a bit. I asked him, can you elaborate even a bit more? And he wants to give some further insights today. Sepp Hochreiter is very well known. He doesn't need not more of an introduction because he invented the LSTM. He is also the head of an AI lab in Graz in Austria, head of the ELLIS Unit or director of the unit there. And he is founder of NXAI, a company which is very successful. And he got, congratulations again, this INNS Lifetime Contributions Award. Really, really great. And when I asked him now, out of all this, what are you most proud of? People would assume, yeah, this LSTM invention. But what he's really proud of is that it's not just a theoretical invention, but they can actually impact the practical world by having set up this company and having this success. And I'm very eager to hear more about that, Sepp. The floor is yours.
Thank you. Thank you for this kind introduction. Perhaps I start with some background. It's not only founding the company, because these times you need private money, you need a company to show that you can compete with some architectures, like with xLSTM. I couldn't show it with public money only, with university. I needed to have a company who has some money to give me the compute to show there are alternatives to attention, as you already said, to transformer architecture. And that's where I'm proud of that I achieved, not only using university resources, but also this private money to show there are alternative architecture, which I will show in my talk. And yes, my talk is about LSTM, but the new version of it. And then I will go into time series prediction. I will try to start my slides, right?
Exactly, yeah. Please share your slides.
And I once achieved this, and I have to do it again.
Looks that's coming, yes.
And to do this.
It looks very good. Go ahead.
But I need a laser pointer, which is not dangerous for you because it's only in the screen. It cannot hurt you. Don't be scared of my laser pointer. It's my laser pointer. Okay. I'm talking about the new architecture, about LSTM, in particular about xLSTM, and what we can do in context learning, especially at the end of the talk for time series. Perhaps I start with what's going on. You already showed what's going on first. We needed hidden Markov models and LSTMs and transformers. and so on. And here, why transformers are perhaps not any longer a choice, your first choice, because they're very complex in terms of computation, and also in memory if you have long sequences, if you have long context. And here you see it was always like, hey, transformers can scale. If you make them larger, you are getting better. But also this law is falling, because you saw it with GPT-5. There were high expectations, but then GPT-5 was not so much better than previous models. Yeah, it's clear, because we don't have more data, we don't have more text. If we don't have more text to train on, we cannot make use of the larger models. Larger models does not help if we don't have more data. And here, perhaps you have to think about alternative architectures, of alternative ways to train, in this case, large language models, or in more general foundation models. Here you also see it at mid-2024. There was this big, huge models here in the middle. You see it as a model size by how large the circle is. But then if we go to the far right, we have very good models, but they're small. They're not so large anymore. And this is what I always say. The scaling laws are over. To scale them up, to make them larger, to get better models. Yes, that was at the beginning. You see it here, GPT-3, and you scale them up. You made larger circles and got get better models. Now this time is over. This is scaling up. We saw it in other technologies, like in computer. You build big computers, big halls were full of computer. Now the same computer you hold in your hand, you have a cell phone, and it's the power of a computer which was in the halls. This is necessary, this is scaling up, to build these very, very large models, to see where are the limits, what can be done, without doing very specific stuff. But now we know what's possible, and now we should go in a direction to make use out of this knowledge. We don't need so large models anymore. We can do it with smaller models, but we can also specialize models. If we have a model on a machine, if we have models which control machinery, these models perhaps don't have cite Shakespeare. They should be specialized to this machine task. Therefore, now, after knowing what's possible, we should bring the AI, these models, to the machinery, into the companies, do more specialization, do more, make them faster, make them real time, and so on and so forth. That's the current trend I'm seeing. Therefore, going from large language models to small language model is tendencies I see. Here in this table, you see advantages. The most biggest advantage is it's cheaper. You save money, but also you can bring the small models to the hardware, to the chips, to the machines. There are privacy issues which are better if you have it locally and don't send your data to a big server, to the cloud. And you can much better customize them. You can much better adjust it to a specific task. And it's cheaper, it's more adaptable, and so on. These small language models, it's now for language, might have their time now, after we saw what the large language models, what they can do. But now we have to use this knowledge. Now we have to apply all these AI techniques. And they will be applied in terms of smaller models on machinery, energy efficient, fast. And that's where we are going here. At the bottom, you see our logo, NXAI. That's a company. This is a company which I founded and via which we could afford the compute to show that's a new technology. It's called xLSTM, standing for extended LSTM, that it can compete with transformers, with attention mechanism. Why we need an alternative architecture? Because the transformer technology is slow, memory inefficient, it's costly, it's expensive, and we need fast and cheap, energy efficient method. And LSTM is used in many industries still. The Google guys told me, hey Sepp, do you know what we are using for translation? We use the old LSTM. We don't use transformer. I don't know whether it's true, but I believe them because if it's on some cell phones, the transformer is a huge beast, and perhaps you cannot tame it to live on a cell phone. xLSTM, the new LSTM, the LSTM enhanced, is fast, memory efficient, and it saves a lot of energy. We don't need nuclear power plants here in Europe to drive our models because they are smaller, faster, memory efficient. What does this give you? With this technology xLSTM, we can go to embedded or edge applications, to really small devices. We can go to robotics, machine learning, and these big models until now don't have big impact on robotics because they're just too slow and too clumsy. We can use it for self-driving or drones, meaning in these autonomous vehicles, you cannot carry a big battery with you. It's much better if you have a small, a tiny model which does everything you needed, but does not use a lot of energy, and therefore you don't need a big battery. And autonomous production systems. What's the disadvantage of transformers? First of all, it's quadratic in the context length. If you produce a text, for every new token, or let's say for every new word you're producing, you have to look back at every word you already produced, or at every word you produced, including the prompt, the user-given prompt. Meaning, if you write a book, if you write down a new word, you start again for producing the next word, reading the book from the beginning, word by word, and then you produce another word. This gives you the quadratic complexity, because if you write n words, for the nth word, you have to look back at n-1 words. And if you think this through, you will see it's something, it gives you some quadratic complexity. Disadvantages are also there are only pairwise interaction, because we have dot products. This is attention mechanism. The attention mechanism, it does a dot product and then a softmax. And actually, it's a similarity search, and you get out the value for which the according key was most similar to the query. It's only a similarity search via dot products. There are no complex interactions. And in particular, there's no abstraction. For abstraction, you need more hints, you need more topics that you say, oh, it's about the kitchen, or it's about the beach. If you have something like sand, water, surfboard, cocktail, and so on, then you, in your mind, the concept of a beach builds up. But not if you have only one word. If you only say sand, it's not immediately clear that there's this abstract concepts that you're on a beach. Therefore, for abstraction, you need more than one single token. xLSTM, yes, it's built on LSTM, it's extending LSTM, but LSTM has stood the test of time. If for Michael and so on, they know it's working, they valued it. There were many deep learning success stories on top of LSTM or made with LSTM from Alpha Star, which was a big policy playing StarCraft, and Dota 5 from OpenAI, also an LSTM policy which played Dota. And actually, LSTMs were the first large language models. Elmo was one of the first large language models. LSTM is linear in context length. I said a transformer is quadratic in context length. LSTM is linear in context length. And that's a big advantage. And it can do complex interactions and it can do abstractions because it interacts with the memory. In the memory, there are different past inputs already mixed up in a complex way, mixed up, and therefore the interactions are more complex. If you interact with the memory, it's more complex than with a single input token. And therefore you can do abstractions, like you have a memory cell, and if you pick up what I said, a cocktail, sand, water, I don't know, sun, then perhaps you have a memory cell which stands for the abstract concept of a beach or of holidays, I don't know. The question here was, if LSTM is good, can we scale LSTM to the size of transformers? Can you do the same as transformers? Is it possible? Yes, it's possible. We have to solve three limitations. I wrote here the three limitations we saw. First of all, inability to revise storage decision, meaning here it's about if you have a new insight, if you have a new best value, for example, it's hard to delete the old best value. Because if you start to delete the old best value, you also delete best values, even if you should keep them, memorize them. Therefore, there's a trade-off between memorizing and deleting. And there's a forget gate, yes, but the forget gate is not sufficient to forget because first of all, the forget gate should be close to 1 to store some values. And now you want to forget, which means the forget gate should be 0. But if you push for the first sequence, for the first task, you want to push the forget gate towards 0, then it unlearns storing because instead of 1 or 0.99, it's 0.95. And it unlearns storing. Therefore, you have a trade-off. Because if you do a gradient update, with one update, you do not perfectly learn. But if you do a gradient update, you reduce your forget gate, but you reduce it also a little bit for storing. This is not desired. You want to store. And therefore, the forget gate has a problem to learn to forget. And therefore, if a new information comes in and you want to get rid of the old information, how do you do this? That's the first problem. The second problem was limit storage capabilities or capacities. Here the problem was you have these memory cells, but these memory cells are only a scalar, are just a number. It's 5, 8 or something. But in 5.8, you cannot store complex things like a whole word or a concept complex. You can only store abstractions, as I said. Abstract thing was this abstract concept to what degree was present or not, but you cannot store which car was it. BMW or was it Mercedes or whatever? You have problems to store precise things because in a single number you cannot store complex things. You need to store a vector. If you store a vector, so you can store complex things also. So occurrence of a specific word. For a memory cell, you cannot store the occurrence of a specific word, except you have as many memory cells as you have words, but then you can store once, but you cannot interact. So the storage capacities are limited, not so for transformers. And the most serious problem was no parallelization for training. The transformer, what they're doing is they're computing all KVs in parallel. They compute for a whole sequence because sentence is already known you're training on. And therefore, for all words, for all tokens, you can produce already the values. The first word and the last word goes simultaneously into the next layer. And then they are collected by the attention mechanism. But you can do everything in parallel, which is not possible for the original LSTM, because the original LSTM, to compute the new gate activations, to compute the new memory activation, it accesses the old memory. Using the old memory content influences how the gates are behaving, influences what you want to store. Therefore, you have to wait to compute the new state or the new state of activations of the gates. You have to wait until the old memory is computed. And this slows you down because you can only do it step by step. And this was the big success story of transformers. This was a big success story of attention because you can parallelize it. You can learn on more data in the same time. You can throw more data against some models. You can scale them up. This was a big advantage. Here, first of all, an example how this forgetting or let's say revising your memory context can go. Here we have a flag of Monaco, and now we are checking in sequence because it's a sequence model LSTM. In sequence other flags. If we find a flag which is similar, we store the population. If we later find a flag which is more similar than the most similar flag so far, we have to store two things: the new similarity score and the population of this country. At the end, we want to have the population of the country which has the most similar flag to the flag of Monaco. Now, let's see what's going on. We find Canada, similarity score 1. Now it's Peru, similarity score 1.5. Greenland, similarity score 2. But the population always changes, if you see. The population goes up and down depending on what flag you think. It's Poland, similarity score 3. It's very similar, 37. Austria, similarity score 4, population 9. Singapore, similarity score 6, population 6 million. Indonesia, similarity score 8, and 281 million citizens. And you saw for the similarity score, it's easier. The similarity score always increased because you only store something if you find a more similar flag. This might be handled, but if this is complex, but it's a monotonically increasing thing. But the population, if you want to store the population, you cannot do it with traditional LSTM because If you store 8 million, then it jumps up to 50 million, then it goes down to 1 million. How should you do this? How should you store stuff like this in a memory cell? You have to delete the memory cell, fill it again. But as I said, forgetting and keeping the memory two sides of one coin, because you cannot learn forgetting while keeping some memory. This is a trade-off. And the way to solve this, we see this LSTM for this nearest neighbor search has a much worse MSE. The MSE is the population you give out, and the transformer is doing well because it's sitting at the end and looking for the most similar flag, which is, you can do it directly. It's a softmax. The softmax puts a lot of weight on Singapore, and you have your number. Transformer is doing very well. And we need something, it's called exponential gating. Exponential gating solves this problem. And xLSTM is exponential gating. It doesn't achieve the performance of transformer, yes, but it gets considerably better compared to the original LSTM. And this is the idea of SLSTM. SLSTM stands for scalar LSTM. You see on the left-hand side the new SLSTM, on the right-hand side the classical LSTM. What are the differences? First of all, I want to bring your attention to this exponential gating. Instead of a sigmoid unit, as for the classical LSTM, we have exponential unit. But this also might lead to some problems, because this can be huge values. It could be very large values, because this is the input gate, which is exponential in this case. And the input gate is multiplied with the cell input. Therefore, these values can become huge. And then the cell state, because it gets these huge values, also this becomes very large, and we get something like Noether numbers. What is the solution? The solution is we introduced another state, that's a normalizer state. The normalizer state keeps record about the size of this input gates. If the input gates are large, this normalizer state becomes very large. If these input gates are super small, this normalizer state is super small. And at the end, we divide the memory cell state, the CT, divide by NT, which is the normalizer state. Meaning now we cancel out somehow the contribution, the huge contribution of the input gate. And we are now, after this division, in the range of the ZTs of the cell inputs. Why is this helpful to device storage decisions? Because if we stored something in a CT, how can we delete this and store the new things? Here, in the limit, think about a very large IT, a very large input gate, like infinity. You have some value plus infinity or almost infinity times ZT. And for the, which means basically only IT times ZT remains here. This previous term is small compared to a huge input gate. For NT is the same. This is small compared to this huge IT. Therefore, the CT is almost IT times ZT. NT is only IT. And now if we divide it, we divide out IT. And here only ZT remains, which is this. Meaning, it's like we only have stored ZT. We have forgotten everything which was previously, because we put so much weight on the current input that we overrode everything what was previous. And this is what I meant with to revise the storage decisions. And if later comes even a larger, a more important value, meaning I need even a larger input gate, the exponential function allows me up to a certain degree to increase it even further, to increase it, to increase it, to increase it. And therefore, there's no end. If something later comes which is more important, I can always increase the exponential function. I know there are numerical issues. We take care about the numerical issues. We normalize it if there was already a large input gate. We subtract the exponential of this input gate to keep it numerically stable. We can increase the exponential function, but still keep it numerically stable because we remove the largest so far seen values from the exponent. And this means to revise the storage decision. Not possible with classical LSTM. Yes, if ft would be 0, you would have the same thing. But if you once start to push ft, the forget gate, towards 0, cases in which the forget gate should be 1 are also pushed to 0, because with one update you cannot get the perfect solution. Therefore, it's not possible to learn to forget on a single instant, at a single time point. We solved this. Exponential gating solves to revise storage decision. Limited storage capacities. Yeah. We know transformer can store whole vectors, all tokens, words which were previously. How to do this? Here, an example where LSTM is really bad and the transformer is really good. We have a word which is super rare. It almost never appears, homeomorphism. In your daily work, probably you don't use it very often, but here's a Wikipedia page. Homeomorphism appears again and again and again, and it's saying homeomorphism is this, and it has this property, homeomorphism is related to this, and so on and so forth. You all the time talk about this new concept, this new word, this new mathematical property. And especially in Wikipedia, we have this, that you introduce a concept, or you're in a specific epoch in art or in music, and you use some words again, which you normally very seldom use. And here it would be good if I can store this word the first time it's used, and if now I want to predict what word is coming, two spaces with it will go over this new word. If I have stored this word, I can predict it here, but only if I have stored it. And so LSTM cannot store this word. It has the single memory cells. I need a whole vector to store whole words. I need a vector because then I can map each word to an embedding, to an embedding space, and then recode from the embedding space the word again. We need a vector memory. Then we can store these words. For this rare token prediction here on wiki text, specifically on this Wikipedia text, we partition the tokens according to how often they appeared in the text. There's this on the left, this very seldom tokens. They appeared less than 1,000 times. Then we have tokens that appeared between 1,000 times and 10,000 times. There are tokens which appear more than 10,000 times. And overall, LSTM and transformer look quite similar. LSTM made big errors, but if you look where it makes errors at these rare words. Because if the rare words come, they come again, and LSTM cannot store these words, the specific words. And it also cannot learn to store it. LSTM has to learn to store stuff, but these words are so seldom that there was no mechanism to store this. Transformer is doing better, or if transformer is not as good as with more frequent words, but still transformer can deal with it and is therefore better. Their tokens have to be memorized, but for language it's good to memorize which words were used, which words appeared. That's one of the essential stuff for generating text. If we now use a memory structure which is not built of scalars, but it's built of a matrix memory with the covariance update rule, we see this xLSTM, which is using this memory structure, the mLSTM, now is in the range of the transformer. Now there's no big difference anymore. And even here, xLSTM is even better. Now we are there. We need this matrix memory. We need this more complex memory. And how does it look like? It's on the left-hand side. On the right-hand side is still the classical LSTM. On the on the left-hand side, it's the new LSTM. And you see a capital C, it's a matrix. C is a matrix. It has a forget gate. And against this matrix, the old value of the matrix, input gate. And here's the outer product. Vt times kt. V stands for value, K stands for keys, and later also the queries came into the game according to the transformer technique. But first of all, if you look only at the first formula, if you remove the gates, the forget gate and the input gate, it reminds perhaps you on something. It's something like a classical Hopfield network with the HEP rule. It's not a Hopfield network, it's a bidirectional network, but it's because otherwise you have K transposed. It would be a Hopfield network, but the same HEP update rules are done for this bidirectional networks. This is more or less the memory of a Hopfield network. That's the idea. But the Hopfield network is now equipped with forget gate and input gate. We control what should be stored in the Hopfield network, and we control whether the old memory should be downscaled. Because we still use exponential gating, we have also here something like a normalizer state. But the normalizer state in this case is really a vector. It's a vector of it times kt. We retrieve the v's by multiplying q's to ct. If q hits a k, that's k transpose times q, and then I get vt. Therefore, k also contributes to how large, to what amount vt is stored. And therefore, it also goes into the memory, into the normalizer state. it because of the exponential value. This is the important part. And now we do a normalization, and it's nt times qt. It's this normalizer state, also multiplied by the qt. But now, because this dot product can be very small or even negative, we take the absolute value and also keep it above 1 for numerical reasons. But this is the mLSTM. We also have an output gate. This ht computed like this is multiplied by output gate, but the output gate is a whole vector. So ht is a vector, single components of this h differently weighted by different components of the output gate. This is the mLSTM. Important, a matrix memory, covariance update rule, which is known from Hopfield networks and HEP rule. And we need the normalizer if we do something like exponential gating. So that's the mLSTM. And now the nice thing is we also get the parallelization because the gates F, I, and O, key values and queries independent of the old age of the old memory content. LSTM, the classical LSTM has this. Here's a F, I, and O, depend on the old HT, but they removed these dependencies. Therefore, the gates and the key values queries only depend on the input. And therefore, we can compute it in parallel. We don't have to wait for this old age. We directly can compute it. It's like the transformer. We lose something which is called state tracking, but we win a lot in terms of parallelization. Now we have done this. I skip a couple of slides. Perhaps LSTM scaling laws, if we compare it to Llama, which is a transformer model from Meta, Mamba, state space model, RWKV, another recurrent neural network. If we go to for 300 billion tokens and to model sizes of 1.4 billion parameters, we perform better than those. I go ahead. Compared to other models on a mass problem, we are better than some models. We are worse than some other models, but the other models are either larger or newer, have better data. If we would train it again, we would also go up to higher values because now the data sets are better. But we have beaten everything which was available as we started learning, but new ones come out, we are worse than this. But we can compete. If we would do it again, we would also get performance of others. But more importantly, why we build these xLSTMs, it's the model speed. Here you have tokens per second. xLSTM can produce 160 tokens per second. And this is for Mamba, for the state-based models. This is another implementation of Mamba. They produce less. Transformer is close, but with context length, the transformer goes down because this is quadratic dependencies on the context. xLSTM only has to access the memory, only have to play with the memory. If you have something new, you interact with the memory and you update your memory. So transformer has to go over the whole sequence. And if the sequence here, it's a sequence length, it has to go over, it becomes longer and longer. The transformer can produce less tokens in a second. And that's a big advantage. And here, if you go in this region, LSTM is already 4 times faster or can produce 4 times more tokens in the same time than transformers. xLSTM is the fastest model. Therefore, also the cheapest model, the most energy efficient model. Here, it's a recent thing. Here we computed xLSTM scaling laws. The paper went out a couple of weeks ago. And this was astonishing. Nobody believes this. Some of the bigger companies now look into it because xLSTM is Pareto dominant over dense multi-hull transformers. Meaning here we have the compute flops. It's for training. It's not for inference. For inference, we are faster anyways. For inference, we are faster because we are linear, transformer is quadratic. This is for training. We are transformer kicked LSTMs from the market because they were faster. Now, exactly in training, it's opposite now. Less compute flop is better, is cheaper. And this is a validation loss on the y-axis. Better is if the loss is smaller. If you're more to the left, then you're cheaper. If you're more down, more in direction x-axis, you have a better performance in terms of validation loss. And what do you see here? For a fixed flop budget, like here you fix the flops here, xLSTM models are better because now we go up and we hit xLSTM model, meaning xLSTM model has with this budget on compute better performance. Or you say, I need a certain loss. Let's say I need a loss of 2.4. Not higher, because then it doesn't work for me anymore. And now I go to the right, then I hit an xLSTM model. This is the cheapest one. This needs less flops, less compute than the transformer models. And this is a shocking result for some, because it means everybody who uses a transformer is wasting money. But it's quite new. It have to be validated by others. Therefore, what we do xLSTM distillation, meaning we have a transformer block. We just replace the tension mechanism by an MLSTM. This is ongoing work for Llama 7B base. We have an xLSTM which is better and faster, but copying by keeping the feed forward heads. The MLP we keep as it is, but only the softmax is replaced by an MLSTM. The softmax is replaced by an MLSTM, but the MLP block is only copied, and the MLP keeps most of the weights. That's the idea of this distillation, and this works for us very well. Therefore, for every open source, it has to be open source. For every open source model, we can build an xLSTM model which is equally good or better. Yeah, xLSTM is already used in industry and so on. This would be a video, but I will only, perhaps I cannot even start it. I need, then I can do this.
Hey, visionary.
How can I help you?
Take off.
I'll start the engines now.
Follow me and tell me what you see.
Sure, I'll do that. I see a person in an industrial area. Yes, there is a house with white cars in front of it.
Thank you for your help. Please land on the roof terrace of the building.
I am now starting to land on the rooftop terrace of the building with the white cars. Landing successful, visionary goes into standby.
This was now, oops, I hope I did nothing wrong. I have to go to laser point, that's not dangerous. Again, xLSTM much faster than transformers. They have a constant memory. Now I showed you also they're faster than transformers at training, or cheaper. Better for a given compute. And I think this technique has high potential for industrial applications. We saw already an industrial application in Spleen Lab. They used xLSTM, but or Vision xLSTM for the drones, because there shouldn't be a lot of batteries, and you have to have this high resolution images because you have to look down to the ground. I think I will skip this thing. Other methods now going out, which are similar to xLSTM in terms it's linear attention, like very popular these days is gated delta net, stuff like this. They have almost something like an input gate, but all these methods lack an input gate. In Blue I made something which looks like an input gate, but it's more like a crew kind of version. The input gate also appears in the forget gate terms. We are the only ones who have an input gate here, which is good for very long sequences because we can select what to store. We don't have to store everything. We can store something without affecting the memory. Others have to store, but they have to affect the memory, which for counting or so is not a good thing. I want to introduce, for the last couple of minutes, TiRex. TiRex is time series Rex. It's the king of time series, and it's a time series foundation model. first of all, what are time series foundation models? How should I explain this? Perhaps let's try me. You know the large language models, you know ChatGPT, Gemini, and so on. How are these models trained? These models are trained by feeding in a lot of text and predicting the next word. It's about next word prediction. And you use all kind of text, all kind of text you can find in books, patents, on the internet, in textbooks, whatever. You grab all the text and learn this large language models on all of the text. And then if you have learned them, you put a prompt, it's called prompt, you do a small text, and it's completing the text. It's doing what it was trained on. Predicting the next word. If you have the next word, you feed in everything with the next word and predict again a next word. That's how large language models are trained. And so large language models, you don't know what kind of prompt, what kind of text you give them, because they have seen so many texts, they will be able to complete it. But now do the same for time series. Let's do the following. Let's grab all time series we have, all available time series, and now train a model. It's called a foundation model. Train a model to predict all time series. What you do something in context. Perhaps you do the last 200 or 2000 data points of a time series in context, and then you should predict the next value, the next data point. Like with transformers, like with large language models, you have words and predict the next token, the next word. Here you predict the next data point. And you do it for all time series, EEG, EKG, traffic, weather, health, whatever you can imagine. You take all time series, finances, energy. There are so many time series. You use all time series and train a big model on them. And it was trained, you give a context, you give the previous value, and you only have to predict the next value. It's the same like with ChatGPT, with these large language models. And what should come out and what really comes out is a time series model. You don't have to learn. You put in a new time series and it's working without training, without knowing where your time series are from. Is it your pulse? Is it your financial data? Is it your heating data? It does not know, but it's working because it has seen so many time series that it exactly knows what would be the next data point. This is time series foundation models are pre-trained on all available time series. It's zero-shot learning. You put only something in context and it's going. Or in context learning, you put something in context and it's learning on what is in context. Both things are actually the same, because you don't know if you put something in context, this is only memorizing a similar time series, or if you put something in context, it's just learning on what you put in context, because it's going over the context and you don't know what's doing actually. Past values are used as context, as prompt. Past values are the prompt. And it's predicting in the future, it's producing new words, it's continuing the time series, it's predicting future values. This is large language models, but now it's the language of machines, it's the language of nature, it's time series. It's not words, it's data points. And we used an xLSTM to build a time series foundation model. It's called TiRex. TiRex can do state tracking in contrast to other foundation models. There are others there. It's only saying that if we use an xLSTM, it's more powerful than, like here, transformers. But it's also more powerful than INNS because it can count stuff. It's some hierarchy, Chomsky hierarchy, where we see this LSTMs, this SLSTMs are more powerful, can store the current state and continue, like so where's your robot arm? transformers cannot store anything because they don't have a storage. They always have to go over the whole sequence again. Here, I will also go fast over this. We have a very fast implementation of the xLSTM. We cannot use MLSTM as a transformer implementation because it has a hidden dependency. Therefore, we can do state tracking, but on the other hand, we cannot make it very fast. But we have a very fast implementation where the recurrent weights in the registers of a GPU. Also, we can make it very fast, but not as fast as you see here as transformers. If you see flash attention here, it's always considerably faster, but ours is this orange one. Flash attention is faster, but we are much faster than a naive implementation. We have fast hardware implementation, CUDA implementation, but also Triton implementation for this xLSTM time series model or foundation model TiRex. It's not true anymore. We're heading the leaderboards. I show you the leaderboard. Here, that's one of the leaderboards, but we're not heading it anymore because Kronos 2 come out. The Amazon guys build up a new leaderboard, and now we are beaten. But in the coming weeks, we will fight back and will be again on top. We are not top. Kronos is now top. But you see, there's this big companies, Salesforce, Amazon, Google, and so on and so on. Here, what's interesting is we are much faster than all the other. Most of them are transformer-based models. We are much faster, and we are not leading anymore. True, but we will lead in 2 weeks. Here, a big fight is going on. That's another leaderboard on Hugging Face. TiRex has beaten all the others. They are perhaps from China, from Alibaba, Datadog, Amazon, Google, and so on. You see it here. Also here, Google tried to, with this Times FM, beat back, and Google is now also leading here. But again, also here, in 2 weeks, we will become top one anymore. This is all data because here it's a big fight going on between Google, Amazon, Alibaba, Salesforce, Datadog, and us, NXAI. We are playing with the big guys. I don't know how long because I heard they build up groups of 100 researchers with a huge compute. I don't know whether we can compete. Here, I'm coming to the end soon. Here, one guy who tried out TiRex, and he downloaded this model, and he did it on the electricity consumption of in Vienna. He used the last year, and then he wanted to predict the next days, the next 69 days, and the forecast was very close to what happening. We were not aware of this guy. This is we were not aware of this task. It's time series foundation model. You take it. It's like with ChatGPT. It doesn't use what you will ask it. Here, it does not use what you put in context. The context is now the blue time series. This guy puts this blue stuff in context and try to predict his energy or electricity consumption the next months or days. And it works. Cool. We did not know this guy, but it's only showing you, you take it, you don't have to learn anything, you don't have to have data, you only have to have a context of a time series and it's working. I already said this, xLSTM is much faster than transformer, constant memory, faster in training, but also faster in inference, of course. better for a given compute, but in particular important, it's energy efficient. You get better results with less energy. So that's the xLSTM landing page, if it's still up. And this is the guys who worked on this project. I'm going back to this, and I'm open for questions.
Thank you so much, Sepp. That was very amazing and quite exciting to see how the race is there and that small labs have a chance, despite many European colleagues always saying we have no chance against the big companies. So I'm very happy to see and congratulate for these races. I assume, I'm very sure there will be quite a few questions. So whoever has a question, just raise your hand or use the chat function so that I see that questions are coming. I have already one, if there's no one else yet raising the hands. Yeah. You mentioned that these LSTM, xLSTMs, they are faster, especially with increasing prefill size. I have a feeling that one of the most important parameters, like your matrix, how big this memory becomes. Is there some, some message? Is it scalable also to become even way bigger, this matrix? So what are your insights?
Yeah, that's a design choice. How this is a C matrix, how large you make it. Now we make it. It's a more or less a square matrix, hidden dimension times hidden dimension, so that we can store column-wise the vectors. But we can make it also larger. But we didn't look into it how large this memory should be. Probably it can have different size for different tasks. But that would be still something to explore. The good thing is the memory stays the same. If you have a sequence of 100 or a sequence of 1 million, you store it in the same memory. It could be that you have 1 million, that it's squeezed and you cannot store everything, or it's superimposed. The quality may decrease, but the memory size stays the same. And so if the memory size stays the same, it's good for some of the companies coming to us that we have a chip, we have some hardware, and we want to fix it. We cannot, like the transformer, they have this KV cache. And the KV cache becomes larger if the sequence is longer. Therefore, it's hard to implement. We have a memory, it's fixed size. If you make it too small, it does not work because everything gets superimposed. If you make it too large, then we use up a memory or a hardware memory, but not exploiting it. But it's a research we also thought about as a scaling laws for memory, because if you can design some memory with all these new recurrent architectures, if you increase your memory, how much improvement you get perhaps for time series or for language. It's not explored until now.
Because there's very often, by the way, I still see no hands raised. Please just raise your hands so that I can see other questions around. But it's a bit of a follow-up on that, because it's very interesting. But if I think now, and we are like in human thinking, right? There are things we keep very, very long in memory, and things we have like a context task, and we know, okay, now I have to remember my seat number in my airplane, but I can forget about it in a while. And normally there are like either I know that I can forget it, or I get the instruction you can forget about it. But did you try ever out if your networks really forget when they should forget, and to investigate a bit what's going on inside of these memories?
Very interesting question, because forgetting is a little bit more difficult, because if you forget it, you cannot recover it anymore. More interesting is what you can do with the input gate. You store something, and now with exponential gating, you can overwrite stuff in your memory. But to write something in the memory to make it more persistent, that we cannot do. We can write it in by a high input gate weight, and therefore it stays longer because it's much higher than others. Because also for humans, if you have emotions, perhaps then you memorize better. If you have fear because there's a tiger, you will never forget it, perhaps. Yeah. Stuff like this, input gate can imitate that you have some stuff there. Another thing, what's happening is if information is repeating, you store something, but then you are reminded on this because something else comes, you put it out, you compute it, and you store something similar on top of this. Therefore, reinforcing your old memory, also changing your old memory. That's the right thing, because if you store a vector twice, you store it on top of the other vector. But if it's not precisely the old vector, you modify your memory. You don't remember the old stuff again. But also for us humans, it could be if you memorize something, if you recall your memory, so more often you recall it, it might also change. It's not always exactly the same. But this happens, that you recall it, you see some similarity, then you store a new value, which is a little bit overwriting your old value. But as you said, I can decide this I have to memorize or not. The input gate can do this to some limits, but yes, that's like revising or fixing. Perhaps I should say you can fix some memories or emphasize some memories. So exponential input gate might do this, yes.
Yeah, interesting. I see there is a question from Ali. Please go ahead, and you can also share your video if you like. Okay. Ali, can you speak?
He's muted, right?
Yeah, but normally people have the possibility to just unmute. There is no regulation.
Okay.
So
Yeah. Am I audible?
yes.
We can hear you.
Yeah, there was great talk, and I'm happy to hear one of the author of xLSTM. There was trained on 7 billion parameters. So I'm wondering, what about the parallelization? That is one of the beauty of transformer models. Either data side, either either from the model side. From hardware side, I mean, transformers are very good in parallelization. So how xLSTM deals such kind of huge matrix when recursion is taking place?
Yes, the idea was here, it's MLSTM, was we looked at transformers and looked what is the difference to transformers. The difference was the transformers can compute everything already and does not have to wait for some stuff previously. And the LSTM has always to wait for some memory context, and with the memory context, you can update the new gates. Let's say, let's take the input gate. We cannot compute the input gate with the original LSTM before the memory is updated, because the input gate also uses the old memory contents for its update. Now we said for the MLSTM, we skip, we don't use the old memory anymore. The input gate does not look at the old memory, it only is looking at the input. But the input in training is already there. You have the whole text. You know all the words. Now I can, if the input gate only depends on the input, I can compute the activation of the input gate. I can compute the activation of the output gate. I can compute the activation of the forget gate. I can compute the activation of the incoming value to the memory cell. Everything I can compute because I don't have to wait for the old memory. If it's there, I still have to collect it, but also softmax have to go over all the sequence. But then the sequence is already ready. It's prepared. I don't have to compute anything anymore. And by not using hidden connections, by not using the old memory content for updating the new values, we lose something, yes, but we are as powerful as transformer, but we are also as fast as transformer because we can do this parallelization. We can compute for all tokens in parallel the values for the gates and for the key queue.
Thank you. I see another question from Mike Tokic. Maybe.
Yeah.
Also.
Hi, Sepp. So this is Michelle from Siemens in Munich. At work I'm also so now investigating time series foundation models, and I'm wondering how many covariates the TiRex model is able to process, and also up to which length you can put data into the context. So that means how many past data you can put in order to do predictions reliably. So what's your experiences?
This are two questions. Perhaps I start with the first one. It's multivariate and covariate. Our TiRex cannot use multivariate or covariate, but we have now a version which can do. But there are different ways to do it. There's Amazon, I said, we are beaten. That's Kronos 2. Kronos 2 use multivariates or covariates. If we're looking in the future, because one covariate could be all holidays. If you know the holidays in the future,
exactly.
It's important. And this is not only covariates, it's also covariates where you know the values, or you have a schedule for your machinery. You know already what's happening in the future when you change the tools or stuff like this. And you can use these covariates. And there are now different ways, and we're exploring this in the moment how to do it. Kronos is doing it by going over by an attention mechanism, going over all time series, by going over all covariates. And using attention mechanisms like a query with the others. And what Kronos is doing, it's learning to exploit the covariates. As it goes over the time series in context, it's extracting the dependencies. It's meta-learning. It's learning a learning algorithm. Kronos learns how to extract dependencies, where dependencies, and uses for a prediction. That's the first thing. And Kronos only achieves this by producing a lot of data with covariates, a lot of data with multivariate, but especially covariate data. You have to produce a lot of data because you have to learn a learning algorithm. If you don't have the data or use real data, it's synthetic data. You have to use synthetic data where you do some correlation, perhaps some time delay or whatever you put in. And this worked well. If you produce the right training data, then you can learn a learning algorithm. So learning algorithm goes through a context and says, yes, if this goes up, this goes down, learns this dependencies. We looking at this one way, but we're also looking at using copulars for predicting the dependencies between time series. One way is going with copulars. Another way is using separating two predictions. We have a prediction in time for a time series, and we have a prediction over the multivariate, over the other time series. Can I predict from the values of the other time series the value of my time series? And like least squares and stuff like this. But the question is, you have now two predictions over time prediction and over the covariates. And the question is how to combine it. We're looking into this, but I'm quite sure that we already have something, but I'm not satisfied because I want to really clearly beat Kronos and these guys. We are looking at this, covariates and multivariates, but there are so many possibilities how to do copulars. There are different copulars. We can build another least square predictor or whatever. To the other question, the context length. That's there with TiRex. We are not so flexible. The context length is now 2048. And what these foundation models do, they put a couple of data points together, a batch, to make tokens, like in language. And what we're using 32 data points. In our case, gives one token. We do
So this is similar to the Siemens GTT, which has patches, non-overlapping patches in the data of 64
Yeah, we don't have overlapping, but okay, it doesn't matter. But we have these patches. Each patch is going into an embedding space, and you embed whole patches. Here now is 2048 divided by 32 gives you 64. The nice thing is our time series, actual time series, going off of patches, is 64, which is good for xLSTM, because if the time series becomes much longer, xLSTM is not so good anymore because it's not so good in memorizing. So we have to switch to mLSTM. We saw mLSTM and xLSTM are similar on this size, xLSTM a little bit better. As soon as the sequence length increases, the sequence length is actually 64. mLSTM is better because it can memorize patches. And xLSTM runs into limitations because it does not have this matrix memory. And we can combine this. We also are looking at this, but right now it's very sensitive how to increase the context length without making a very long time series. If you make a very long time series, xLSTM is not so good equipped for it. mLSTM would be better. And now we want to make a hybrid of M and xLSTM. And then we can increase the context length. But increasing the context length is important because also models who increase the context length got better results. We work
also. So due to this token modeling, would it also become possible to obtain some kind of uncertainty about the predictions? So because you have a discrete probability distribution over tokens, so that means you could have like a range in the upper and the lower bound on the predictions.
We already have all these things as point prediction, but you have also probabilistic predictions. What we do is we have 10 quantiles. We do quantum prediction. We don't have only one output head, but we have actually I think 11 or something like this. But so here's also a trick. So new trick is even if you have to provide 10 quantiles, it's better to predict 21 quantiles. And then out of the 21 quantiles, compute the 10 quantiles you have to give the leaderboard. This is also a new trick we saw, which is helping. But we're predicting quantiles. This quantile predictions has a separate error function, and we have more heads. And therefore, we have this probabilistic prediction.
Cool. Thank you very much, Sepp.
Yeah, great.
There's also a question from Gonzalo in the chat. I'm not sure if you want to read it by yourself. It goes in the meeting chat. It says
okay, I see.
For robotic.
Gonzalo Marquez, yeah, right. Here, this is exactly this is in robotics. There's exactly what this question is addressing. That transformers have to go over the whole context again and again because they don't have a memory. So the idea would here is that we do state tracking. We can store the state of a robot. The state of a robot could be how the motors, but where's the arm located, stuff like this. If we can do state tracking, meaning we can store the state of a robot, we can do very, 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 very long sequences as long as our state estimation remains the same. Perhaps we have to correct our state estimation because perhaps we get camera input where you see as arm is somewhere else than we estimated with our state. But we don't have to go over so long sequence because we store the state. And this gives us a huge advantage. For example, we saw it in hydrology. In hydrology, we have super success stories because we can store the state of the system. We predict how much water is in the river. If it's raining, water is in the soil, water is in the underground basins. Water could be also in snow, which is melting later, or in glacier. And then from the weather, the temperature, and so on, you predict how much water is in the river. And LSTM is doing very, very well because it can track the state. It can guess how much water is stored in the soil, how much water is in the snow. And then later the sun shines and how fast is the snow melting, and this melting water goes into the river. It's very, very, very good because it could capture the state. What is the state? Where's water stored? In the soil, in plants, in snow, or underground in these basins or underground rivers. And here we see a huge, huge advantage over transformers. And I think the same holds for robotics, because we can track the state of the robot. Where, in what angle is the arm? What angle is the current angle? At what position is the end of the arm? We can track and store, memorize in what position and how the robot looks like. And therefore, we don't have to go over long sequences. If we have a perfect storage of the position, we only need the new motor instructions and use the old state to predict the new state. And therefore, we can skip long sequences, or we go over the long sequence and track also states. Therefore, long sequences, if it's working, would not be a problem for LSTM because it can track the state. Even if it's Markov, transformer have a problem because they cannot store the state in what states they are. They always have to begin. They always have to go over all KV cache again, and then they don't store anything. Even here you say it's non-Markov. For Markov, we can track the state. For non-Markov, we have to memorize some key events from previous stuff. It's also important, we have also machinery where we have to know how hot is a device. Because if it was used very in a fast or in a very heavy way previously, heat is still in the tools. But right now you have to memorize. Yes, previously I used it heavily or on a very hard metal like a driller. You have a driller, you used it for very thick material, and now your drill is hot. But now you have to memorize it. This is not Markov because in the actual state you don't have perhaps a temperature sensor, and there it works. It also works to keep the state, but also in non-Markov state to memorize some events from the past. And also this transformer can do. I'm absolutely sure that xLSTM for robotics is much better and can overcome these problems described here, where you have this huge KV matrices where you have to go over it again and again. And you have always to deal with it. What is this PCMB? It's bringing in a memory. It's like what xLSTM already has automatically, so bring it in externally to have a memory to memorize the state.
Yeah. Okay, very nice. We are now converging towards the end of the official recording time, so thank you so much again. I will now conclude this webinar by a short summarization. Too much stuff. Just to mention, this webinar is part of a longer series of webinars organized by the INNS. And if you follow inns.org, you see what will be the upcoming webinars. We have already one scheduled on the 11th of December, and this will be by Sajal Luri, who was the INNS Young Investigator Award winner. And I'm quite excited to hear from him also about AI safety a bit. So join our webinars, join INNS. You will get